This was the year 12 test from Tuesday, whenever it was, yesterday, whenever this video goes up, I don't know. We're going to integrate this here. We need to get it into power form so it can actually be integrated. So root x is x to the power half. And now, of course, this can just be integrated, raise that to a 4, divide 2/3 by 4. You can just do that on a calculator. Raise that to 3 over 2, divide 6 by 3 over 2. Again, a calculator will do that. X integrates, sorry, 1 integrates to x, and then remember the plus c. Otherwise, you will lose a mark. And that's the first question done. Question 2, I would just always draw vector questions. Position vector means that it's starting at the origin. So 4 minus 5 is over here and down here. So that's the vector OA. And then B, position vector again, starts at the origin. Minus 5, minus 2. And we're trying to get from A to B. So we're doing this journey here from A to B. Now to do that, we can go backwards along this one and then forwards along this one. So we're going to add these two vectors up, but change the signs of this one because we're going backwards along it. So it's going to be minus 4i plus 5j plus this plus this. Of course, these are minuses, and so they stay as minuses when we just add them in. And we end up with this, and we get this, which we can just see visually, right? To get from here to here, you're going backwards 9 places on the x-axis from 4 to minus 5, so that's that there. And then you're going upwards 3 places on the y-axis, right, from minus 5 to minus 2. And you can also just do it that way. AB with lines here means the modulus of or length of, so just look down here, AB. It's across 9 and up 3 is what we said, across 9 up 3. So the length of this is just going to be Pythagoras, 9 squared plus 3 squared square rooted. Your calculator will just give you this straight away, and you'll have your answers to that one there. First principles is in the formula book. Here it is. So if we define f of x to be x cubed, you can say f of x plus h, replace the input with x plus h, replace this x with x plus h, you get this. And now we're ready to just put it in the formula. So it goes in there, f of x plus h is this one, f of x is this one. Do some binomial to expand this out, or you can just do right over here, x plus h, x plus h, x plus h, and do some actual expansion. It's up to you, but either way, you should end up with this. The binomial goes 1, 3, 3, 1 for this, which you probably just know. And then, of course, we just trade off these powers. Now, this cancels with this here, and we get this. We can divide all these terms by h. This h cancels out. This one just goes to an h1. This goes to an h2. And as h goes to 0, this term goes to 0 because it will be times by something that's basically 0. And so does this one, 0 squared, basically. And so we just end up with this term, which is unaffected, and we get 3x squared as our answer to f dash of x. Good. Question number, I don't even know because I didn't put any question numbers here. Cool. We have a binomial expansion of this. The way that I imagine you guys have been taught this is just to do 2 to the power 6 first. And then the next term is going to be 6 choose 1. Technically, this is a 6 choose 0, but we don't really care. 6 choose 1, take 5 of those and 1 of those. Always make sure these two numbers add up to this number here, 6 in this case. 6 choose 1 here, and then the next one will be 6 choose 2, and then 2 to the power 4, and then this to the power 2. You can just type all these things in the calculator, 6 choose 1, 2 to the power 5 times 3 quarters, 6 choose 2 times 2 to the power 4 times 3 quarters squared, and you'll eventually get all of this. Of course, you can do plus dot 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 if you want to, only once the first 3 terms, which are going to be these 3 things, having typed that into a calculator. And now it says explain how you could use this to find this. So we just want this whole thing here to the power 6 to be this thing to the power 6. So set this equal to this number here. Take away 2 times by 4 divided by 3. And so we just need to explain here that if we substituted an x as minus 0.1 into this, we would find an estimation for this here. It's an estimation, of course, because we're missing these extra terms that would matter less and less because when you cube this, it gets very small and so on, but they would matter a little bit. But anyway, this one here is the first of, I think, the really tough questions. There are 2, I think, quite tough pure questions in here. But anyway, this one here, so replace the cos squared. I mean, I'm hoping we have remembered this formula. It's not in the formula book. We really need to know this. You take away sine squared from both sides, you get this. You can put that in for this one here. So when you're solving equations of this type, always replace the squared one by using this identity here. Put it in there, expand out. You get something that looks a bit like this maybe. If you want to, you can just proceed with this. Otherwise, you can set something like y to be sine theta. And so y squared is sine squared theta and replace that in there. And then if you're more comfortable dealing with this, put that in a calculator. It looks like it factorizes, but it doesn't. Put it in a calculator and get this. Now I'm going to write that as decimals. I'm going to put it as like this. And the reason I'm doing that is because now that I have y as this or y as this, I can replace y with sine theta again, which is what it should be. And by just very quickly picturing or drawing the sine graph, I can see that sine varies between -1 at its lowest and 1 at its highest. So it's never this. So that's not actually going to be a natural solution. So let's get rid of it. Let's do sine inverse of 0.566 in a calculator to get this. And 0.566 might be here. And what the calculator is telling you is that the first solution it came across when it looked for answers to this was 34.5. But of course, there's more solutions that come along later. So we have to work out what those are. The first one, if this is 34.5 across from here, we can do 180 minus 34.5 to get this one here. The graphs are always symmetrical in this way, so we can just take away that first one to get to here, which will be this one here. And then we're actually looking all the way until 450 degrees, which is a little bit further than what I got here. But of course, every 360, the graph just repeats exactly what it did before. So what I can do is I can take this result here and just add 360 to it, and I'll get the one that's just off the page here. So just add 360 to that, we get that. I could add 360 to this one to get the next one, but I noticed that if I do that, I'll be well over 450. So I think these are the three solutions that we'll have here. Now, a student attempts to solve this equation here. And firstly, they write tan as sine over cos. That's legit. We times everything by cos. That's also cool. 0 times by cos is still 0. And now from here to here, they've just removed the sine x. You can imagine they've divided by sine x. And of course, 0 divided by sine x is still 0. But the problem is, imagine that sine of x was 0. Imagine if sine of x was 0. So you'd have 3 times 0 minus 5 times 0 times whatever equals 0. Well, that checks out, right? 0 minus 0 is 0. So sine of x equals 0 is a solution here, which vanishes when you remove the sine of x. So if you ever divide by something like sine of x here, in a case like this, you just need to say, okay, what if it were 0? Of course, sine of x being 0, look at the graph, that means x is 0. Between 90 and minus 90, there's no other solution there. And we have this solution x equals 0. Check that in this original question, but it checks out too. So that's a missing solution that they've lost and haven't accounted for. They've done the next thing fine. They've put the 3 over divided by 5 and got this here, except think about the cos graph between minus 90 and 90. Cos is symmetrical around the y-axis. So if we're looking for solutions of, well, this is 0.6, isn't it? So it's up here somewhere. We've got this solution which the calculator ran into because it did a search going to the right, and it found 53. But of course, by the symmetry, we can also say that minus 53 is also a solution within this range here. So we're also missing this solution here. When you're identifying errors like this, the best thing to do is always state the correct answers entirely. And that's always the safest way of picking up marks, I think. Anyway, now we have this question here. So we're still looking at the cos graph, still equaling 3/5 up here somewhere. Now, if we just do, we can ignore this. Like, you could think about this in terms of graph transformations and what this does to the cos graph. I'm not going to do that. I'm just going to take cos inverse of both sides and find my initial solution, which is the same as what we found up here of this. But now I'm going to say, okay, let's just find a bunch more. So 53 is the first one. The next one over here will be 360 minus 53, using that same symmetry idea that we did before. So that would be that there. And then, of course, it's repeated every 360. So I could do 360 plus this 53 for that, and then 360 plus this to get that. And that's 4 solutions. The reason I'm stopping at 4 is because that's the first 4 positive ones here. Those correspond to these here. But of course, now I can just take away 40 and divide by 5 to all of these. So each in turn, I'm going to take away 40 from all, and then I'm going to divide all by 5. I eventually end up with all these. So that's just all of them taking away 40 divided by 5 all at the same time. And this is the 4th one here. So the answer will be 125 to the nearest degree. Now, I could have thought about the roots over here as well, like this minus 53 roots that we discussed earlier. Except if you imagine this was a minus 53, when you take away 40, that makes minus 93. Divided by 5, that's a negative number. And of course, all of these will just give you negative numbers, and we weren't interested in negative solutions, just positive ones. So that's why I searched this way and not this way. Sometimes you would have to do a bit of a search in both ways. Like, imagine that was a minus 40 or like a minus 100. If you took the minus 53 and then added 100 to it, you get to a nice big positive number. So that would matter. So sometimes you do have to search in both directions, but not in this case. Good. So the last of the pure questions. This is just a banging question that just uses a load of different areas of maths. If you get given a point like this means x is 2 when y is 10. So let's just put those values in here. Y, of course, you can just replace with this f of x. So just put 10 equals a times 2 cubes plus 15 times 2 squared and so on. Sort this all out, you get this, which isn't very helpful because it's got 2 unknowns. But let's read the next line. The gradient, now as soon as you see the word gradient, that's dy by dx or f dashed of x, however you want to write it. And even if you don't understand what comes next, just work that out. Just work out what this is, differentiated. But what this says is the gradient at here, so when x equals 2, we don't really need the y equals 10 information, but the gradient dy by dx at x equals 2 is minus 3. So what I can do is I can differentiate this. I could have written f dash of x, it doesn't matter, but differentiate this to get this, and then when x is 2, so substitute x is 2 in, dy by dx is minus 3, so replace that with minus 3. And what's nice about this, of course, is that the b differentiates away, and you just end up with an equation in A, which actually just solves to exactly what they wanted you to get. And once you've got that, you can put that into here, and you'll get the b value as well. And we'll have b is 44, and yeah, we'll have this first bit done. Hence, so C has no stationary points. Stationary points are when dy by dx equals 0, or f dashed of x equals 0. So we've already got dy by dx, and I can replace that a with a minus 2 to get this. So all I've done there is replace the a with minus 2 and set dy by dx equal to 0. That's all I've done. And I'm just going to solve this. But of course, I mean, there's lots of ways you can do this. You could just put this in a calculator and see that it gives you complex roots and concludes that there are therefore no real stationary points. Or you could, I've just timed everything by minus 1 there. You could think about b squared minus 4ac. If that were to be less than 0, there would be no roots. And that's the rule that we know, isn't it? The discriminant check. So, okay, b is 30. It's actually minus 30, but when it squares, it doesn't matter, does it? Because they both square to 900. Take away 4 times this, and that's a negative, so therefore it's less than 0, and there are no roots. So you could make that conclusion there as well. That would be one way of doing it. Now, lots of you don't watch my YouTube videos regularly at all, but if you did, you would know that I just have a rule on this channel, which is that we never do polynomial division. So we have this f of x here. I've just replaced the a with a minus 2 and the b with a 44, as we discovered in this section. Now, you could divide this by x minus 4 polynomially. I just will absolutely refuse to do that. I'll just write it as x minus 4 times some quadratic with coefficients that I don't yet know. So quadratics, of course, x squared and x and something. I'm leaving blank coefficients, but I think I can figure them out because, like, I'm supposed to expand this out and make a minus 2x cubed. Now, the only terms that would multiply here to make an x cubed are these two, so that must be a minus 2, because how else am I making minus 2x cubed? Now, same thing over here, right? I have to make a plus 44. The only way to make no x's is to times the two constants together. So what times is with minus 4 to make plus 44? Well, that would be minus 11. And I'll have that one as well. So my cubic's taking shape here. I'll just call this coefficient d for now. And then I'll think about how I'm going to expand this to make x squared terms. So I know I've got 15x squareds in the expansion, but looking at this, how do I make x squared terms? Well, I either do this times this, which will give me 8x squareds, positive 8x squareds, or I do this times this, which will give me dx squareds. So therefore 15, lots of x squared, is equal to 8 of them plus d of them. Just comparing where I would get x squareds from, which of course means d is 7, and this will be my factorized form. When you get good at this, it's so much quicker than polynomial division, and it's why I refuse to do polynomial division. But anyway, we have this here. Hence deduce the coordinates of the points of intersection of this thing. So, okay, now this is a crazy way to write the number 1/5. And when you see it as 1/5, you think, okay, that's a stretch. Horizontally, factor 5. It's pulling the graph outwards horizontally by factor 5. Right? So why don't we think about what this graph looks like that we've been dealing with before, and then think about what would happen if we stretched it out. So, okay, this graph, we've got all the information. We found A, we found B, we've got it in factored form. And think about the graph sketch then. That shouldn't have come up again, but whatever. It's got a root at 4, this graph. Of course, it's got a root at 4. It's also got a y-intercept of 44. And a really important, this scale is not in line with the scale, but it doesn't matter. A really important thing that we figured out here was that C has no stationary points. So this is a cubic, it's a negative cubic, so it starts over here somewhere and finishes down here somewhere. And it's never stationary. It never actually bends, or well, it bends a little bit, but it's never flat. So it just sort of looks a bit like this, maybe, right? Like it's never actually completely flat. It just sort of kind of smoothly makes its way through each point. That's a terrible sketch, but it's absolutely not going to matter. And the point that I often try and make in these videos is the quality of sketches is often not important, right? As long as you just have it in front of you, that's where you're going to get it from. Now, so that's what this looks like. This curve that we've been sketching here or we've been talking about here, only intersects the axes at 0, 44 and 4, 0. Right? Those are the only 2 points. Now, when we stretch this out factor 5 horizontally, this point's not going to move. So that's still going to be 0, 44. This is going to stretch out factor 5 and go from 0, 4, from 4, 0, where the root was, to 20, 0. When it stretches out factor 5, times it by 5, and we get 20, 0. And that will be the only 2 places. You're not going to invent any more roots or intercepts here, are you? So you're just going to end up with those 2 places there. Now we hit the mechanics section, so we've got, you want to kind of develop a sixth sense for questions like these. I know you had a topic list, so you absolutely didn't need it here. But when you're doing like an actual mechanics paper and you're not, or like a proper test that doesn't come with um, a list beforehand, you want to develop a sixth sense that this is just a Suvat question. Like somehow you just need to read this and immediately think, oh, this is just about Suvat. Um, so okay, we've got Suvat is here. We've got all the equations in the book. It's got an initial speed of 14.7. Uh, the first thing we're dealing with is it goes upwards and downwards. Imagine you're firing it from this position here. It goes upwards and downwards, and you're looking for the time it takes to get to the same position it was. Now, in that case, its displacement is zero. Now, the distance it's traveled isn't zero, and we'll deal with that later, but its displacement is zero. If you move somewhere and come back again, your displacement is zero. You essentially haven't moved, is what that's saying. So yeah, displacement zero, initial speed is 14.7. Now the final speed is actually minus 14.7, but we actually don't need that right away, so I'm not going to bother arguing that. Acceleration is downwards, it's minus 9.8, because I've considered that one to be positive, it's going upwards, so this will be minus 9.8, and the t is just big T, they've said. And of course, we can get the equation that doesn't have v in it, and we should be able to solve for t here. It's just this equation here, there, and you actually, this is similar to what we saw earlier. You can divide by t here, which is what I've done. The reason you're allowed to do that is because, like we said before about that sign, if you divide it away, then you have to consider the case of what if it was zero. But like if t was zero, I know it's at a because that's literally what it tells me in the question. So I know that I'm not losing a solution that I need because t is zero is just the initial condition there, what it was at the start. So that's not important to me. Anyway, we can solve this and we get t is 3. We'll have that done. Now, the total distance traveled, I chose to do this in a way that maybe is different to other people. But I said, okay, let's find out how far it goes until it's at the top of its journey. So let's look for an s value. Its initial speed is this. Its final velocity, right at the top of its arc, its velocity momentarily is zero because it's just momentarily hovering above the Earth, not with any speed, and then it will start coming back down again. So if I look for the distance, the displacement it goes until it gets to velocity zero, that will be the upwards vertical displacement. Acceleration is still minus 9.8, and t I don't care about, and I don't need it because, I mean, I could argue it's 1.5 because it's just going to be half of this, but I don't need to do that because I can just look for the equation that doesn't have t in it because I know all these values here. And we'll use this equation here using s as just a little less maybe. I'm using this one here. We can solve this and we get s as this. Now that's the distance it goes upwards and stops in midair. And so the distance it goes back downwards until it's at the starting position, that's just this times 2, right? The total distance traveled is up 11 meters and then down another 11 meters for roughly 22 meters in total. Now that's for the first 3 seconds because it takes 3 seconds to do that up and then down to where it was before. So we've got 1 second more to go. So I'm going to do one more Suvat equation. I've got 1 more second to go. Acceleration is still the same. Initial velocity, I didn't bother arguing this earlier, but when we go up and then down and we're in our starting position, initial velocity is just minus 14.7. It must be because of conservation of energy. Like it's got a certain amount of energy going upwards. If it's in the same place again later, it must have that same velocity going downwards because it must have the same energy because the potential energy is the same because it's in the same position. So okay, by conservation of energy, I know that must be that. Its final velocity I don't know or care about. A is minus 9.8 and the t is 1 extra second we're doing here. And I'll look for the s. So this equation here again, because we don't have v, just stick it all in and we'll find the extra distance that it goes downwards in that extra second. Now I can just make that a positive 19.6 and add it to this. So I've got 11 meters up, 11 meters down, another 19.6 meters down, add those all together, and we get this total distance that we'll travel. When you're talking about refinements to models, always just say something about the particle being the fact that this model is particle, and therefore you're ignoring its dimensions. It's just always a go-to answer that will always score you a mark. So just write that. The last one then is about a lift. I've made a video about these kind of questions before, so I'm going to say a very similar thing here. You could add all the stuff in here. So it's a lift with mass 40, so that's 40g is the force coming down. This is mass 10, so 10g coming down. You've got a tension in the string pulling the thing up, and it's accelerating upwards at acceleration 0.2. So that's that. I'm not going to deal with this picture. I'm going to turn this into a car and caravan question because I like them more. So I'm going to essentially take this picture and rotate it to the side like this. So we've got tension going this way, acceleration also going this way, and then these ones coming this way. And I'm going to imagine those are like the resistances to the car and caravan in those kind of questions. And the reason I'm doing this is just because I prefer doing this. I've invented an invisible string that connects the cage and the block, and it's the tension in that made-up hypothetical string that's the answer to this question here. But now I can just do this question in the same way that I do all the questions that we did that come earlier in the chapter, which is just, okay, F equals ma with the entire picture. That cancels out the F's. I called these tensions F, by the way, just because we already used T, so I just called them F for force. Anyway, consider the entire picture. We've got force is this, minus this, minus this. Technically plus this, minus this, but that'll cancel, so I don't need it. The total mass is this 40 kilos plus this 10 kilos, and the acceleration is 0.2 in that direction. So, okay, I can sort this out, and I'll solve for T as this. And that's cool. So now I have T as 500. And now to get the force here, that's the tension in the hypothetical string. So let's focus in on half of this picture. I chose to focus in on this half. And now I can do F equals ma again. F minus 10g equals this mass only, which is 10 times 0.2. And we'll solve for the F is this here. And that'll be the entire paper. Thank you for watching. I hope that helped. And I'll see you next time.